So this is really the interesting part I wanted to get to. How does the wave carry the energy with it? Remember we started waves carry energies and waves carry information? How do they do that? And there is a very good explanation on how that happens. So energy could be kinetic and potential. The two energies that we're concerned about are kinetic energies and elastic potential energies when we talk about waves traveling around the string. There are two main things I'm going to talk about. This point, I'm going to call it point A, and that point I'm going to call point B. Is the distance dx the same for both points A and B? If you look at just dx, is it the same? And the answer is yes. However, look at your string. Is the string different between these 2 points? One place, it is not stretched at all, right? The top one, the element B. Do you see that's not stretched at all? Whereas when you look at point A, it's extremely stretched, correct? That means that the energies at these 2 points must be different. So what I can tell you is that the kinetic and elastical potential energies. Have you ever thrown a ball up into the air? What happens eventually to that ball? It stops for a second at the top and then it starts coming back down? Is that what happens? So think of this as that point. The kinetic energy, so if the speed of the ball is 0 at the top, what is its kinetic energy? 0. So that means at the top, the kinetic energy is 0. Now, what causes elastic potential energy? If I have an unstretched string and I take that string and I put it down here, what will happen? Absolutely nothing, right? Because it doesn't have any potential energy to do work. So the potential energy of an unstretched string at the top will also be 0. Whereas at this point, it has maximum stretch, so its kinetic energy will be maximum, and its potential energy, which is its elastic potential energy, will also be a maximum. Which means that in order for the string to go from point A to point B, something has to happen. So the energy gets transferred from point A to point B in terms of the tension that changes. Okay? When it is completely sitting by itself at the top, how much is the tension? Almost negligible. But when it's stretching, is the tension more? Yeah? So the tension gets maximized and the tension gets minimized as the string stretches and moves forward. So the speed of a transverse wave depends on the tension that it takes with it at different points and the kinetic and potential energy, which is why this complicated formula has come about. All that means is A is just the amplitude, V is the speed, mu is just mass over length, which is called the linear mass density, and omega is our angular frequency, and T is just tension. So the formula that I would like you to write is P equals 1/2 A squared mu V for velocity and omega squared, or 1/2 A squared omega squared square root mu T T. These are the two formulas. Yes. Oh, so average power is the amount of energy the string takes with it. So think about average power as, so power is change in energy over change in time. So combination of kinetic and potential energy that is carried by the string as it moves forward. And that is the main purpose of a wave, right? To transport energy. And that's what it does. And the amount of energy that it transports depends on its tension. I don't know, I just really like this picture. I think this is a really cool picture. It explains so much. It explains how waves take energy with them. It's just fascinating. So now that we have done this, we should do a problem. A transverse sinusoidal wave with frequency of 100 hertz is traveling along the string with linear density of mu 0.5 kilograms per meter that is held under a tension of 50 newtons. If the maximum amplitude is 1 centimeter, find the average rate of energy transport. So first of all, what is the question giving me? It's giving me frequency of 100 hertz. It's giving me mu of 0.5 kilograms per meter. It's giving me tension of 50 newtons and an amplitude of 1 centimeter. Uh-oh, there's a problem. What do you have to do with 1 centimeter? 2 meters, right? So how many centimeters in a meter? 100. So it will give me 0.01 meter. And what's the formula I'm going to use? It's asking me for the average rate of energy transport, basically power. Average rate of energy transport. So which formula should I use? I think I'm going to use this one, A squared omega squared square root of mu t. Problem, I don't know omega, but I do know omega is 2 pi f. Did they give me f? Do I know T? Do I know T? Yes. Do I know mu? Yes. Do I know A? Yes. Can I calculate omega? Woohoo. Done. Anybody have an answer? I can tell you my answer is about 98.5. And the units for power are what are called watts. And power is defined as the rate of change of energy, which means power is the rate of change of energy per unit time. Energy is measured in joules, time is measured in seconds, so power is measured in watts. So the electrical bill comes out in kilowatt hours. That is how much 1,000 watts did you spend in an hour in that given month? Just by the way, it has nothing to do with music, but it's something you should know for life.